Okay, so Rahul's given me the honour of bringing this meeting to a close, and it's all surprised that so many people here. And this, because it was mainly a pedagogical meeting, that's what attracted me here particularly. Most of my comments are addressed to students, so even if there aren't so many here, and we've 10 more students. So. Anyway, so maybe 8 or 9 years ago, I got an email from somebody in Korea, and he wants to know whether it's okay if he translated my data analysis book into Korean. And I said, fine, if you really want to do that, but if it's for your own use, that's fine, but if you're going to do something with it, then you should ask OUP. And he said it's just for himself, but he said, what do you know about, do you have any thoughts on Peele's pertinent puzzle? And as usual, I'd never heard of it. So I looked it up, and I used it as an illustrative example in a talk I had to give in Lisbon a few years ago. So if you want to see this written up, actually you can look it up. So first of all, I'll describe what the puzzle actually is, and it involves least squares. So I'll just remind you about least squares, and it relates to the problem. We'll try and understand the problem, and then the answer to the puzzle led me to ask some further questions, and that was the phrase Raoul couldn't remember, whereas Laplace is viewed as that probability theory is nothing common sense reduced calculation. My PhD supervisor put it as data analysis, simply dialogue with the data. You don't say, I've analysed these data. When you analyse data, you're asking a particular question. And just because you ask one question doesn't preclude the possibility of asking another or several others. Indeed, the answer to one may suggest a better question to ask. And so, hopefully, when we go through this, you'll see this process of having a dialogue. It's just illustrative. A bit of fun, really. Anyway, so this is Peele's puzzle. This is Robert Peele, who was at Oak Ridge, put forward this problem. There are a lot of words here, but basically there are two measurements of the same physical quantity, and the result of one measurement was 1.5, the result of another was 1.0, and these measurements have got error bars, and they're also correlated. And the way he describes this is, well, I don't actually quite understand it, and that'll be part of what I do with it later. But so you've got these two correlated measurements of the same physical quantity, and you want to estimate what that quantity was. So that's straightforward enough. But what troubled Peele was the following, that when he used least squares, he found that his best estimate of this quantity was 0.88. And the measurements were 1 and 1.5. So his best estimate lies outside the range encompassing the two, and that really bothered him. And so his question was, under what conditions is this the reasonable result that we sought to achieve by using advanced data reduction technique? Okay, and I think this is the earliest quotation of Peele's problem here. So first of all, let me remind you of least squares, and let's check that that's indeed what happens, because it does look rather odd. So I can summarise what Peele said in this way. We're interested in some quantity mu, and we've got estimates, experimental estimates of it, d, so just the two measurements, so it's just x1 and x2. And we've got some estimate of the uncertainties and correlations between those measurements. And when you give a variance and an error bar, implicitly in the back of our mind, we've got that this variance here, the error bar squared is actually this variance of this quantity here, this error bar is that. And if they're correlated, then that's the correlation coefficient is epsilon. It's a number between +1 and -1. Okay, well, we'll come back and put Peele's numbers in a moment.
X1 and X2 are a vector of values?
No, they're these two measurements. X1 is 1 and X2 is 1.5.
I don't understand how you can have two variances.
No, there's the error bar on the first measurement, the error bar on the second measurement, but the two measurements are not independent of each other. So the third thing that tells you how the two measurements are correlated. You know, for example, if you did one measurement and you didn't actually do it again, you just gave the same result again, then they'll be 100% correlated. Yeah, so it's just not independent measurements, that's all. Right, so
But they could be the result of a set of measurements whose mean and standard deviation is given by.
so the means are x1 and x2, right? And yeah, it could be indeed, and that's the variation of that set, and that's the variation of that set, but the two sets are not completely independent. Normally we assume our data are independent, but they don't have to be. They can indeed be correlated, and this was the problem in this case here. So we're trying to estimate mu, so in the spirit of these squares, we'll just say something that doesn't very quickly, and go to the simplifying extreme and say it doesn't change at all. What about the likelihood? Well, if the information we're given are expectation values of the squares of deviations, then you can use the principle of maximum entropy to assign the probability. You get your familiar bivariate Gaussian. So it takes the form e to the minus chi1 squared and these normalization terms here. And chi1 squared is given. So this is a column vector and that's a row vector, and here's your symmetric matrix, covariance matrix. It looks complicated because usually we're dealing with data where the noise isn't correlated. So usually we're dealing with a case where epsilon is 0, and epsilon is 0, then the square root term goes away because it's just 1, and this becomes diagonal. It all becomes much easier. But it doesn't have to be 0, but in order for the quadratic form here to represent ellipses rather than hyperbole, the modulus of epsilon certainly has to be less than 1. Okay, so we're actually interested, oops, I cut and paste the wrong thing here. This should have been probability of mu given the data. Here's the probability of data given mu, so I put it at x, treat it as that scale of mu. So we've assigned we've assigned a likelihood. In fact, we made the assignments which are implicit every time you use least squares. So that's why it's a least squares estimate. And if you then try and find out where the maximum of that is, with that uniform pi here and that Gaussian likelihood there, all you need to do, because this minus sign, is find out the value of mu, which minimizes this quantity. So differentiate chi squared with respect to mu, set it equal to 0, and it gives you this for your best estimate of mu. So it involves the two measurements x1 and x2. It also involves the two error bars and the correlation between them. And I've simplified the algebra, and I called this combination alpha, and I called this combination beta. So it's alpha x1 plus beta x2 divided by alpha plus beta. And you can also calculate what the corresponding uncertainty in your estimate of mu is from the second derivative, chi squared with respect to mu calculated there. And you should just check, this is an exercise for the student, that if you put epsilon equal to 0, this does reduce to the simpler formula that you're used to. And if you then even make sigma 1 equal to sigma 2, that should reduce to the even simpler formula that we're used to.
Shouldn't we go with sigma squared?
Sorry?
What's that? I thought the weighted average is always go like 1 over sigma squared.
They will do. If you put epsilon equal to 0, it will turn out to be that. Because I've been on the limit. Yes. Yep. Anyway, so again, it's a comment for the students. When you're trying to learn this stuff for the first time, my recommendation is don't try to jump in at the deep end. Right? Try the simplest problems where you know the answer and try to work through it. And that's what I do in the book steadily. And much like quantum mechanics, there are only a few number of problems you can easily do analytically. And as in quantum mechanics, after you've done the particle in the box and the hydrogen atom and the harmonic oscillator, you either have to start using approximation methods and numerical methods and so on. And the same is true in data analysis. There are only a few that you can do simply, and then you either have to use approximation methods or numerical methods. But don't confuse those approximations or numerical methods with the principles, and that's where doing the simplest problems first helps, because then you're not encumbered with practical details. You just see the principles as they are. Anyway, so if you plug in the numbers for Peele's data, x1 is 1.5, x2 is 1. As I say, I don't quite fully understand how he had represented, I don't fully understand what he means by all this, but I looked at other people who looked at his problem, and this is what they think it means, that sigma 1, the error bar on that first measurement, is x1, that's 1.5 times the square root. The error bar on this measurement is 1 times this square root, and the correlation coefficient between those two is 0.8. And you plug in these values into the formula that I've written up here, you indeed get 0.88 plus or minus 0.22. And the plus minus 0.22 doesn't, that's sufficient that the estimate could easily be within 1 and 1.5, but your best estimate is certainly not between those two values, which doesn't usually happen and is a little bit disturbing. So let's try and understand.
I'm very sorry to be so dense, but when I said epsilon 0,
Yeah.
the equation becomes sigma 1, sigma 2 times x1 plus sigma 1, sigma 2 times x2. It's not right, you know. Then we don't get away with some dollar point, it's just the average of x1 and x2.
Okay, well, I thought I'd transcribed it correctly. It's possible I made a mistake. Well, I'll check it with you later, and I think I got it right in the paper anyway. Okay, so if you stare at this result for a little while, assuming I got this correctly, you can actually find the conditions under which your best estimate will be between the two measurements. And that condition is that the correlation coefficient has to be less than the smaller of what these two ratios. And if you look at what we had for sigma 1 and sigma 2, if you look at this thing, this side here becomes 2/3. So if the correlation coefficient had been less than 0.6666, our best estimate would indeed have between 1 and 1.5, but the value that Peele used was 0.8, so the correlation is actually very high. Sorry? Yeah. So that's a row matrix, x1 minus nu, x2 minus nu, and you've got the same, it's transposed as a column matrix, and this is the covariance matrix, and that's why that's the correlation coefficient epsilon.
The problem is I've drawn two samples from binary house.
Yes.
And I want to find out what the best estimate.
Yeah. Yeah. So it's the usual thing if you've got two measurements of the same quantity. The thing that's different is when we normally do it, we assume that these two measurements are entirely, the errors in them are entirely independent. They're not correlated. In this particular case, they have to be highly correlated. And that's why it's happening, that's what I was going to try and point out. Anyway, so from the formula, if epsilon had been less than 2/3, we would have got a number between the two, but the correlation coefficient is high, and that's why it doesn't have to satisfy that. But is that a problem? And should we really be that disturbed by this? And actually the answer is no. If you remind yourself what this correlation coefficient is, well, that's the definition here. I just simplified it. So it's the expected value of the deviation of the variance of x1 and the variance of x2. But because these are variances, these are positive and the denominator is positive. And then you've got the expectation value of the product of the deviations in x1 and x2. And so as epsilon goes to minus 1, epsilon will tend to go to minus 1, or be negative, if the sign of one of these, if delta x1 is positive, delta x has to be negative, and vice versa. So as epsilon goes towards minus 1, it tells you that the deviations have to be opposite. If one is overestimated, the other has to be underestimated. If it's uncorrelated, if it's epsilon, then that means on average this product is positive as often as it's negative, and so you get the uncorrelated result. Knowing the sign of delta x1 doesn't mean that you're inclined to see this positive or negative. It could be either just as often. But as epsilon goes to plus 1, so they're positively correlated, that means that these two tend to have the same sign. If one is positive, the other's positive. One's negative, the other's negative. And that means the sign of delta x1 and delta x2 tend to be the same. What does that mean? That means that your best the measurements are either likely to be both overestimates or both underestimates. And if that's the case, your best estimate is going to be on one side or the other of both of them. It ends up being on less than 1 because the error bar on the other one is much bigger, so the square deviation is smaller if you're on this side. So it's having understood the problem, although it looked a bit disturbing to start with, it shouldn't be. It's entirely down to correlation. The correlation told you that either both measurements are overestimates or are underestimates, and so you're not surprised you're on the wrong side of it. But going back to, so that's fine, so we reproduced this thing, we even understood it and decided it isn't really a problem given the information. But it did sort of bother me because I found this a little hard to understand. And one thing I noticed is that the errors are all given as fractional errors. And it led me to wonder, is that significant? Does that just happen to be how it's stated, or is there some significance? For example, when we did the problem before, our interpretation was that this error bar represents, we've got some estimate of this variance, some estimate of that variance. But everything is written in terms of fractional errors. Is this really the information we're given? Is the information that we're given in Field's problem? Here I've assumed we're dealing with Field's problem by making these two numbers the same, because it isn't his problem, it wouldn't be in general. But is it the case that we know the expected value of this relative error, the expected value of the variance of this relative quantity, and so on? And in this case, then Field's problem, that x1 and x2 are the same, s is that, and epsilon is still 0.8. Well, let's just suppose it is. How things have changed if that's what he really meant in giving that information. Well, being given information on the relative error is equivalent to being given the error on the log of the quantity. Because if you differentiate y equals log x, you get delta y is delta x over x. And so when we were given the expected variance of quantity, we used the principle of maximentropy to assign a Gaussian to that quantity. If we are given, and so being given this is equivalent to being given the log of the quantity, so the principle of maximentropy would suggest we make a Gaussian not in x, but in terms of log x. And so let's look at everything in log space. That's the more natural space if this is indeed the information we were given. So the analysis follows in a very similar way, except if you look at it, I've changed my background information. That involves my interpretation of how the errors were given. And so before I had I1 for my previous interpretation, now I'm using subscript 2 for this alternative interpretation of the information that was given. And I just use this because that's the same as log x1 minus log b, of course. And in Peel's case, because that and that are the same, I could take that factor of s squared outside, and this matrix here becomes much simpler. And to keep in the spirit of least squares, I'll now assign a pi that's uniform with respect to the logarithm of the parameter, and you get the posterior by multiplying these two. So again, these are still the implicit assumptions you use when you use least squares. The only difference now is we're doing least squares in log space, not in linear space. And so if you like, by taking log, we're assuming that we're dealing with magnitudes. So if you want to do least squares on magnitude quantities, you should actually do it in log space rather than linear space. Anyway, you can work through it, and you can find that the maximum of this quantity is given by log of the geometric mean, and that's the error bar. If you plug in the values for Peel, then you find that your best estimate log mean is 0.2, and that's the error bar. This is in log space. If you were to transform it back into linear space, in log space this is exactly a Gaussian, the possibility is a Gaussian. When you transform it back, it's no longer a Gaussian, but it's a reasonable approximation to 1. And if you do that, your best estimate now is 1.22 plus 0.26. So perhaps even Peel wouldn't be so disturbed now. But of course the problem is, I don't know which of these two interpretations is the correct one. The best thing to do is go and talk to Peel if he's still alive. I was in Oak Ridge a few years ago, and a few people remembered Peel because I wanted to talk to him and asked him what he meant. I suspect he'd say, I don't know, I just made it up. But anyway, this may be a problem. I asked one question because there's an ambiguity. I made one set of assumptions, got one answer. I had a different interpretation, got a different answer, and now I'm not sure. So what do I do with that uncertainty? Well, as usual, if there's an uncertainty, we just go back to probability theory, integrate out the thing we're not sure of. So what I really want to know is this posterior probability. Probability from you, given the two measurements and the statement of the problem, but independent of either interpretation, whether the interpretation is I1 or I2. So that's what I want, and I can get rid of the I1 and I2 by marginalizing those two. So if I write down the probabilities for mu and I1 and add it to probability mu and I2, then those two go away because I marginalize over the two possibilities, and I'm given the estimate of mu, just given the statement of the problem, irrespective of either statement. All right, now how do we get these things? Well, as usual, we'll go back to the rules of probability. So each of these is just j equals 1 or j equals 2. So this joint probability can be written as a conditional probability, quoted mu, given d and ij and I. There should be an I in here, but I've omitted it because once I know that the correct interpretation is ij, then I is not quite so relevant, so I just drop that. And the other term would be the probability of ij given the data and I, and using Bayes' theorem, it turns around here. All right, so that's what we need to do. And so we're going to have a probability. We're going to have to all this complicated term. What bit's relevant? Well, there's a bit here which depends on which interpretation did we like before we considered the data. Before we had really any information on what we wanted. This is where you should really go out and ask Peel, because hopefully if you went to ask Peel, he'd say it was this one. And once he tells you it was one interpretation, based on the information, one of these will turn out to be 1 and the other one will turn out to be 0, and so you just concentrate on that analysis. But since I wasn't able to get in touch with Peel, and I don't know which one he meant, for simplicity I'm just going to assign equal probability to both. So if I assign the same probability to this quantity, which is the same, and this quantity here on the denominator doesn't depend on I1 or I2 either, so that's just another normalization constant, so it's just going to be proportional to that times that for j equals 1, plus that times that for j equals 2. But what are these quantities here? Well, this quantity here, which says what's the probability of mu given the data and given the first interpretation, was the first problem we analysed. Probability of mu given the data, given the second interpretation, was the least squares and log space that we dealt with. So what we have to do now is take an average, a weighted average of those, but it's weighted by these quantities. And these quantities are the quantities I mentioned in my first lecture, but you'll have forgotten them. They are actually the denominators in Bayes' theorem for this posterior. So when you write down Bayes' theorem for this posterior probability, we normally write it as a proportional to prior times likelihood in the miss out denominator. The denominator you miss out is precisely this term. Likewise, this is the denominator for this posterior probability. And at least some of us give that denominator the snappy name of evidence. But in the literature, other people call it other things. They might call it the prior predictive, or the global likelihood, and all sorts of things. But some of us think we should just call it the evidence. And of course, the evidence is just the normalization constant at that times that, integrated over all the possibilities of mu. But the slight problem now is that whereas our estimate of mu, given those data and interpretation, doesn't tend to depend on our range over which we assign a uniform prior, as long as it's large enough that the likelihood isn't truncated. When we have to do this integral, it will matter, because the integral has to go to mu. But luckily it won't matter too much, so as long as it's within something sensible, it'll be fine. So here we are. I did it, show you a few graphical examples. So this is from interpretation 1. Yeah, won't take me longer than 10. So this is interpretation 1. And I've assigned a prior which is uniform in linear space here, because this is interpretation 1, 0 and 3. Here are my two data points. It's that with this error bar, that with this error bar. But these are correlated, but I can't really represent that correlation in this diagram. But it's, and the posterior probability looks like this. It is Gaussian and well-defined by 0.88 plus or minus 0.22. But the corresponding evidence factor there is minus 3.35. That's the logarithm of that denominator term. The evidence values on themselves are meaningless. They're really useful when you're comparing two things. So it's only the differences in their logarithms or the ratio of the values that are meaningful. They're not meaningful without that context. Here's the same problem. The only thing I've sorry. There we go. This is the same thing. The only thing I've done different here is I've increased my prior range. Rather than going from 0 to 3, I've gone from minus 5 to plus 5. And the posterior probability, although it looks different, that's simply because the scale's structure, otherwise it is identical. The only thing that's changed is because I've got a bigger prior range, I've got a bigger thing to calculate the average, but the evidence to integrate over, the evidence value has changed to indicate that. It isn't changed by log a lot, it's changed by, I've increased this from 3 to 10, and I think the change is probably going to be the natural log of 10 over 3. Okay, here's the same thing in the other interpretation. In the other interpretation, we were doing everything in log space. So in log space, I put a uniform prior over here. Here are the two data values getting correlated. Here's the posterior probability, and there's the evidence value. So it's the logarithm of the denominator term. If I have a different prior range in my log space, you get the same posterior probability because I haven't truncated the likelihood. The only thing that's changed is the evidence has changed slightly. Of course, what we needed to do was to take a weighted average of the posteriors when there are two evidences. And so that's what I've done here. I think what I did was, you have to think about what the relevant prior is here and what it is in the other case. But I think I made them the same range. But of course, if I want to take the log of it, I can't actually make that 0. So I think I probably chose point. I did the two possibilities. One was going from 0.1 to 3, any log space, it's uniform with respect to log of that and log of the other one. And I also did it for the other case where I go from 0.01 to 10. Yes?
Why should the range on view be independent of the interpretation?
It need not be. I just had to pick some values for illustrative purposes, and I just thought I'd do that.
But then I can manufacture any ratio of evidences I want by changing my range of views.
Absolutely, you can do indeed. So just as in what probability you assign depends on what prior knowledge you have, what range you assign has to depend on the relevant prior knowledge you have. I didn't have any, so just for the sake of illustration, that's what I take. And these evidences only depend logarithmically over the range, so as long as you get by some order of magnitude, that's fine.
I mean, if you say my prior evidence says U has to be between 0.5000 and 0.5001, then you're going to get a number in that range.
No, so what I'm saying is between the log and the linear interpretation.
Yeah.
No, you can change.
Yeah. Very natural.
Yeah. You could do indeed, because for the linear interpretation, there's no reason why the low limit could be negative, whereas for the other one, it has to be negative. But it's not going to change a lot, and it's just illustrating what happens. So that was for the first range. So this is the posterior probability of the first interpretation of the errors on the data. This is the posterior probability from the second interpretation of the data. And I weighted them with their evidences, and of course the total posterior probability is given with this blue line. And that's the same thing for that wider range. And it looks more different than it is because the range is scrunched up, but the change is absolutely fairly minor. So, your best estimate has shifted a little bit to that side, but it's developed more of a tail. So your best estimate might still be a little bit on this side, but you're less willing to exclude the possibility that it's on the other side. Anyway, so what I was trying to do there is just show you that when you get some data, it doesn't make sense to say we've analysed the data, this is the result. When you analyse data, you're asking a particular question, and it's important to understand what question you addressed. What were you given, what have you seen, what simplified approximations have you made? And it's only in that context it makes sense to say this is then what I conclude. And just as in normal life, if I ask you a question, you may well come back and say, well, that depends on what you mean by. And that's very often what probability theory does. You ask a question, which hypothesis is better given the data, and it comes back and says, well, it depends on what you thought beforehand. Well, so what did you think? So that's an example of that. But equally well, if I ask a question and you give me an answer, I might say, well, yes, but what I really meant to ask you was this, because from your answer it's clear that what I've asked or what you've addressed isn't what I had in mind. And so your answer to the first question might help me to formulate a better question, one that I really had in mind, and I can ask that. But there's no limit to how many questions you can ask. And it's in that sense that I agree with Steve Goff that it's all very open-ended. It's really a dialogue with the data. That's all really what you're asking. And I'm going to stop there. And thank you very much.
Yeah. So that's very nice talk. If I were to do model selection with the same data, then I would like to understand the evidence factors correctly. The first interpretation is more likely.
Yes, that's right. But not hugely so. And you don't have to choose one or the other. You just take the weighted average. If one is overwhelmingly more probable than the other, it will essentially focus on that one. If they're comparable, it will take the appropriate weighted average between the two.
What I'm asking is like equal priors.
Yeah.
The basis not actually is the first
They do. But probably only by a factor of 3 or 4. You're not talking hundreds of thousands.
So what does it imply? No, because it's not much.
Well, it says that if you really had to choose between these two, you couldn't. You favour one slightly, but you wouldn't want to bet too much on it, so don't rely on it. Yes.
I thought your second interpretation of the statement of the problem is quite generous, because to me it's very, very strange to specify the size of the error bar in terms of the value that you happen to have measured. right? I mean, the error bar is typically a number that's associated with mu,
Yes.
right? So it's either relative to the size of mu or it's not relative to the size of mu, in which case it's either not logarithmic or logarithmic.
That's right.
But to make it relative to the value of x that comes out, this I find very
That's true, but it's the approximation we usually make. When we create plus on y's and so on, the plus on the square root anything shouldn't be the square root of the number of measurements. It should be the square root of your estimate of mean. But there's many problems. They're not vastly different. To linearize the problem, that's what we did.
Do you think it does make a difference here?
I wouldn't have thought greatly, but you can try it. Can be third interpretation.
Okay, let's thank them once again. I guess Roger and I will say a few final words before we are on board. So, from my side, thank you all very much for coming, the speakers and the participants. The meeting is exactly what we have been hoping for, I think. And if you thought it went smoothly, a lot of the credit goes to whatever meeting. I'm very impressed with the organization from a distance of 150 kilometers, and they're tolerant of the ambiguity and the error bars and so on. And everything we said, our institute administration is great as always, and in particular, our registrar Professor, the administrative officer K.V. Shankaran, and several others whom we've been dealing with on a daily basis. A lot of students helped us out whenever we asked, in particular, to open Sunday when we became ready the previous day and sort of took a great personal interest in making sure everything is as it should be. So, thank you all very much once again. Roger.
Well, I have very little to add. Now that said, most of it needs to be said. I think I'd like to add that I did absolutely no part of the organization because I was away. So I think we should all thank Rahul once.
No, that was true only for the last 10 days or so, but all of you have agreed to comment, and so.
I think maybe with the, before we finally discuss, maybe we could take a photograph.
Yeah, one last photograph. I was carrying the camera for a couple of days, but I didn't think of taking it out. A lot of people have gone so much. You want to go out?
Maybe or
Maybe. Can we go to the portico and get a photograph?
let's like it.